So today we're going to be looking at the chemical properties of carbonyl compounds, specifically the reaction of carbonyl compound with hydrogen cyanide. Okay, but before we do that, let's remind ourselves of what a carbonyl compound is, right? Carbonyl compound has this C double bond O, right? This is referred to as a carbonyl carbon or a carbonyl carbon, right? And here I used R to represent either hydrogen atoms or some carbon chain, right? So the C double bond O, if it's bonded to a hydrogen, it's an aldehyde. And if it's bonded to carbon atoms either side, then it's going to be a ketone. Now the first thing to note is that in a carbonyl compound, we have the C double bond O, right? So we have a pi bond, we have a double bond here. That means that carbonyl compounds are unsaturated compounds, okay? So they're unsaturated compounds, therefore they undergo addition, okay? They undergo addition. Now the second thing to note is if we look at that carbonyl carbon, again, this is our functional group in carbonyl compounds. This could be an aldehyde or a ketone. And what we notice here is that the carbon has a partial positive charge and the oxygen has a partial negative charge, right? The CO bond is a polar bond. Now in this bond, the oxygen is more electronegative than carbon, so that's why it gets a partial negative charge, and the carbon gets a partial positive charge, right? And this delta positive carbon, okay, this delta positive carbon attracts nucleophiles, okay? It attracts nucleophiles. So because carbonyl compounds are unsaturated, they undergo addition, okay? And because they have a delta positive carbon, this delta positive carbon reacts with nucleophiles, okay? So carbonyl compounds react with nucleophiles. So therefore, we can say that the name of the mechanism via which they react is nucleophilic addition, okay? The mechanism that we're going to look at is nucleophilic addition. So we're going to look at the reaction of carbonyl compounds with aqueous hydrogen cyanide. Reaction with HCN aqueous. Okay, reaction with HCN aqueous. So we'll start by looking at the example of ethanol. Okay, we have CH3CHO. This is ethanol, right? It's an aldehyde. And this guy can react with aqueous HCN. This guy reacts with HCN aqueous, okay, to form a hydroxynitrile, okay? So the compound that we're forming is referred to as a hydroxynitrile. So the compound that we get is CH3, CH, OH, and then CN. This reaction is carried out in the presence of a catalyst. We can use NaCN aqueous or KCN aqueous. We can use NaCN aqueous or KCN aqueous. Okay, and we heat. So this is the nucleophilic addition of HCN. Okay, nucleophilic addition of HCN. So we're adding on this H and we're adding on a CN. So the C double bond O, the C double bond O becomes a COH. Okay, the C double bond O becomes a COH. So we get a single bond here, okay, instead of a double bond, right? The pi bond breaks. And the CN also adds on to the carbonyl carbon. The CN also adds on to the carbonyl carbon. This type of a compound is referred to as a hydroxynitrile. The reason it's referred to as a hydroxynitrile is because we have a hydroxy group, right? We have this OH group and we have a CN bonded to this carbon. Hence it's called a hydroxynitrile, right? Nitriles are compounds where we have the CN group. And obviously when we say hydroxy, we mean that we have this OH group. This compound in particular is called 2-hydroxy, okay, 2-hydroxy propane nitrile, okay, 2-hydroxy propane nitrile. So your main functional group here is the CN, right? That's your nitrile. So you have a 3-carbon chain, hence propane nitrile, right? 1, 2, 3, 3-carbon chain, propane nitrile. And we have an OH group on carbon number 2. So this is 2-hydroxypropane nitrile. And again, this type of a compound is referred to as a hydroxynitrile. Okay, so the reaction with HCN forms hydroxynitriles. Okay, to form hydroxynitriles. Now this reaction proceeds via a nucleophilic addition mechanism. Okay, it proceeds via a nucleophilic addition mechanism. So over here, the cyanide ion is your nucleophile. Okay, Cn minus. Okay, and it's the carbon atom. It's the carbon atom that carries the negative charge. Okay, this carbon atom is the guy that will end up bonding to the carbonyl carbon. Before we look at the mechanism, we're going to look at where this nucleophile comes from. Okay, so if you look at HCN, okay, HCN is a weak acid. All right, HCN is a weak acid. And when we say something is a weak acid, okay, we mean that it ionizes partially to form H plus ions. Okay, so HCN is a weak acid. Okay, HCN is a weak acid that ionizes partially to form H plus ions and Cn minus ions. On the other hand, NaCN or KCN, our catalyst, right, that's a salt. So when we dissolve KCN in water, for example, right, KCN, on the other hand, will ionize completely. Okay, KCN is completely ionized in aqueous solution. So because HCN is a weak acid, right, it ionizes partially to form H plus ions and Cn minus ions. Okay, we can say that very few cyanide ions are produced. Very few cyanide ions are produced when HCN ionizes, again, because it only ionizes partially. It's a weak acid. On the other hand, because your catalyst, KCN or NaCN, ionizes completely, we can assume that the cyanide ion, okay, the cyanide ion comes from the catalyst. Okay, it comes from the catalyst. Okay, because that's your primary source of cyanide ions. Okay, so we can initially assume that the nucleophile, the cyanide ions are coming from the catalyst, that is KCN or NaCN, because KCN or NaCN ionize completely, and so we get a lot more cyanide ions. As a result of the ionization of KCN or NaCN than we do from the ionization of HCN. So the initial nucleophile is provided by the catalyst. That's why we're going to need this catalyst, because HCN doesn't ionize completely. Okay, it won't produce enough cyanide ions for this reaction to proceed at a reasonable rate. So now let's look at the mechanism. So here we have the cyanide ion, that's our nucleophile. Okay, and we have our aldehyde in this case, that is ethanal. The carbon atom has a delta positive, partial positive charge, and the oxygen has a partial negative charge. In the first step of the mechanism, okay, the cyanide ion, that's your nucleophile, attacks this delta positive carbon. Okay, it attacks this delta positive carbon, and at the same time, the pi bond between the carbon and the oxygen breaks. Okay, and we end up getting an intermediate. Now, in this case, our intermediate, okay, has a negative charge. Okay, so the electrons from the pi bond end up as a lone pair on the oxygen. Okay, so the oxygen ends up with a negative charge, and then we have our CH3 and we have our H. So what we get over here, is an anion intermediate. Okay, we get our intermediate. Okay, and in this mechanism, our intermediate is an anion. Okay, so it's referred to as a carb anion intermediate. Okay, our intermediate has a negative charge. Now in the second step of the mechanism, the hydrogen from the HCN adds on to this oxygen. So we have HCN. Here hydrogen has a delta positive or a partial positive charge. We have a partial negative. And what happens here is that the oxygen attacks this hydrogen, and this HC bond breaks heterolytically. Okay, and we end up making our product. So what we get here is we get C bonded to a Cn, bonded to a CH3, bonded to a hydrogen, bonded to an OH. Okay, and we also get Cn minus again. So this over here is our product, right? We have 2-hydroxy propane nitrile, 1, 2, 3 carbon chain. So that's propane nitrile, and we have an OH group on carbon number 2. So this mechanism is the nucleophilic addition of hydrogen cyanide, or HCN, to form a hydroxynitrile. So over here what we've done is we've added an HCN. And what we notice is that the cyanide ion that we had initially, has been regenerated. Okay, so what we can say over here, is that the catalyst has been regenerated. So we have to show this catalyst being regenerated because, of course, a catalyst will not be used up at the end of the reaction. Okay, so over here again, NaCN or KCN aqueous are catalysts. So in this particular example, okay, if we notice, the product has a chiral center. Okay, and in nucleophilic addition, if the product has a chiral center, okay, it means that a mixture of optical isomers has been produced. Okay, so in this particular example, okay, instead of getting one single product, we actually end up producing a mixture of optical isomers. The reason why is because this nucleophile, the cyanide ion, can attack this trigonal planar carbon from either side. Again, this carbon has trigonal planar geometry, right? The carbon has trigonal planar geometry, right? So if you imagine a triangle flat on the screen, right, the nucleophile can attack this carbon from the back or the front. Okay, it can attack this carbon from the back or the front, and because the product has a chiral center, okay, when the nucleophile attacks from the back or the front, we're going to get two different products with different three-dimensional arrangement of atoms in space. Okay, so we end up producing a mixture of optical isomers. Okay, so what we get over here is this. To show optical isomerism, we have to show the carbon atom with this tetrahedral geometry, right? Specifically the chiral carbon here, that's the carbon that we're looking at. This carbon is bonded to an OH, a CN, a CH3, and an H. Okay, so this carbon is bonded to an OH, is bonded to a CN, is bonded to a CH3, and it's bonded to a hydrogen. Right, so that's one of your products, and then its mirror image is non-identical to it. So our other product in this particular reaction is the optical isomer or the enantiomer of this compound. Again, enantiomers are just non-superimposable or non-identical mirror images of each other. Okay, so what we're getting here is we're getting a carbon with an OH. We have a CN. We have a CN here. We have a CH3. And we have an H. So we can say here is that a mixture of optical isomers is produced. Okay, a mixture of optical isomers is produced because the nucleophile, in this case the cyanide ion, can attack the trigonal planar carbonyl carbon, okay, trigonal planar carbonyl carbon from either side. Okay, from either side. So if this nucleophile was to attack this trigonal planar carbon from the front, okay, we'd get one of these enantiomers, and if it was to attack this carbon from the back, we'd get the other enantiomer. Okay, and both of these are equally likely. Okay, it's equally likely that it could attack from the front or the back, and therefore we get a mixture of enantiomers in equal amounts. The next example that we're going to look at is the example of pentane 3-one. Okay, we have CH3, CH2, CO, CH2, CH3. Right, this compound is pentane 3-one. And I'm going to react this guy with HCN aqueous, okay, in the presence of a catalyst. In the presence of a catalyst, again, I can use KCN aqueous or NaCN aqueous. So we'll just go with KCN aqueous, and I'm going to heat. So over here, our product, okay, again, what we have is we're making a hydroxynitrile. Okay, so what we get here is we get CH3, CH2, okay, and then this C double bond O, okay, the C double bond O becomes a COH, and that carbon also bonds to a CN. So we have CH3, CH2, and then we have this carbon that's bonded to an OH and a CN. Again, this is the nucleophilic addition of HCN, nucleophilic addition of HCN. And then that carbon, okay, that carbon is bonded to another CH2, CH3, CH2, CH3. So how do we name this compound? Now over here, again, the nitrile is our main functional group. It's our principal functional group, right? So the nitrile carbon will get carbon number 1, and this is carbon number 2, right? And then we can say this is carbon 3 and this is carbon 4. Or we can say this is carbon 3 and this is carbon 4. It doesn't matter, right? We get a 4 carbon chain either way, whether we look at it this way or we look at it this way. So we have 1, 2, 3, and then 4. So we have a 4 carbon chain, right? So that's butane nitrile. And then we have an OH group and an ethyl group on carbon number 2. We have an OH group and an ethyl group on carbon number 2. So this would be 2-ethyl, 2-hydroxy, butane, nitrile. Okay, 2-ethyl, 2-hydroxy, butane, nitrile. Now again, the prefixes have to be written in alphabetical order. So keep in mind that the CN over here is a C triple bond N. Okay, the CN over here is a C triple bond N. Okay. If you wanted to write down the structural formula for this, right, we can say CH3, CH2, C, and then this carbon is bonded to an OH, a CH2, CH3, and a CN. So this carbon is bonded to an OH, a CH2, CH3, and then a CN. So this is the structural formula. Okay, and if you wanted to show the skeletal formula for this, we can start by looking at the name, right? We have butane nitrile. So 1, 2, 3, and then 4 carbons. So you have a 4 carbon chain, right? Butane nitrile. So we have a C triple bond N. Okay, we have a C triple bond N. And then we have an ethyl group and an OH group. We have an ethyl group and an OH group on carbon number 2. So again, the nitrile carbon will be carbon number 1. That's your principal functional group. Okay, it'll always be carbon 1 because you can't have a nitrile in the middle, right? Nitriles have to be on a terminal carbon. Okay, so this is carbon 1, and carbon 2 we have an OH group and an ethyl group. Okay, so on carbon number 2 we have an OH group and we have an ethyl group. So this is the skeletal formula for this compound. In this case, we end up producing just a single product. Instead of a mixture of optical isomers, because our product doesn't have a chiral center, right? This carbon is not a chiral center because it's bonded to 2 ethyl groups. For it to be a chiral center, the carbon has to be bonded to 4 different atoms or groups of atoms. So here we just get a single product instead of a mixture of optical isomers. As far as naming this compound is concerned, okay, we're going to consider this 4 carbon chain as the parent chain, okay, because the parent chain has to include the primary functional group, in this case the nitrile group, okay, the CN over here. So our longest chain that includes the CN is a 4 carbon chain, okay, and the nitrile will be assigned carbon number 1. And again, the mechanism for this reaction is nucleophilic addition, okay, the mechanism for this reaction is nucleophilic addition. Okay, so let's look at the mechanism here, right? For the mechanism, again, we have nucleophilic addition. Okay, mechanism is nucleophilic addition. Okay, so what we have over here is we have, again, the cyanide ion, right? That's our nucleophile. That is coming from the catalyst. Okay, we can assume that it comes entirely from the catalyst because HCN ionizes partially in solution. It doesn't produce enough cyanide ions for this reaction. Okay, so we can say that the cyanide ions come from the NaCN or KCN catalyst that we're using in this case. And we have our carbonyl compound. Okay, so we're going to show that carbonyl carbon. We have a C double bond O, we have a CH3 CH2 and another CH3 CH2. Right, that's pentan 3 on. We have a delta positive, a delta negative. The cyanide attacks the delta positive carbon. Okay. Cyanide attacks the delta positive carbon and the pi bond breaks. And again, we end up making a we end up making our carb anion intermediate. So we get a C, O minus. Here we get the Cn. Okay, and then we have a CH2, CH3, and we have a CH2, CH3. And then the second step of this mechanism, okay, the second step of the mechanism, the H from HCN adds on to the oxygen. Okay, so what we have here is this oxygen attacks the delta positive hydrogen. Okay, so the oxygen attacks this hydrogen and the HCN bond breaks, the bond between the hydrogen and the carbon breaks, and we end up getting our product. Okay, we end up getting our product. So again, for the product, okay, I'll just write down the structural formula. There's a simpler way to write down the structural formula. We have a carbon atom. We have a carbon atom that's bonded to two ethyl groups. Okay, so we can also say CH3, CH2 twice. And then that carbon is also now bonded to an OH and a CN. So again, what we've done here is we've added HCN. Okay, we've added HCN. And the catalyst is regenerated. Okay, so we have to show the catalyst being regenerated. Okay, so that means again that this Cn minus that we got from the catalyst in the first step, okay, is regenerated at the end of the reaction, and therefore it is not used up during the reaction. So here I've shown a simpler way of writing down the structural formula for this compound. Okay, you can show the two ethyl groups separately as well, but it's easier to show them. It's easier to show them together. Okay, because they're two identical ethyl groups on this carbon. So again, because this nucleophilic addition mechanism is a two-step mechanism, okay, because it's a two-step mechanism, okay, if we look at the reaction profile diagram, or the energy profile diagram for this reaction, we have to clearly show that it is a two-step mechanism. Okay, so here I have my reactants. To begin with, I have CH3, CH2, twice on a CO. Okay, again, the CO is bonded to two ethyl groups, right? So this can be written as the structural formula as well. Okay, and this guy is reacting with HCN. Those are my reactants. I have the first step of the mechanism in which the cyanide ion, the nucleophile attacks the delta positive carbon and the pi bond breaks, and I end up making this anion intermediate. Okay, I end up making this anion intermediate. And then I have the second step of the mechanism, right, where the H from the HCN adds on to the oxygen. Okay, the H from the HCN adds on to the oxygen, giving us this OH group. So we end up making a hydroxynitrile. Okay. So here I have my product. Okay, here I have my product, which is CH3, CH2 twice, and then COH, CN. So here we have our carb anion intermediate. Okay, that's this anion over here. Okay, this is our intermediate. So we get a negatively charged intermediate in this mechanism. Okay, on the y-axis we have energy or enthalpy, and on the x-axis we have reaction progress or reaction coordinate. So now let's go back to the earlier example that we looked at, right? That was the nucleophilic addition of HCN. That was the nucleophilic addition of HCN to ethanol to form 2-hydroxypropane nitrile. Okay, now this nitrile, okay, this nitrile can be taken and it can be hydrolyzed. Okay, we're going to look at the hydrolysis of 2-hydroxypropane nitrile. Okay, as an example, hydrolysis of nitriles. So over here we can have acidic or alkaline hydrolysis. Okay, we're going to look at acidic hydrolysis first. For acidic hydrolysis, we can use dilute HCl. Okay, and we can heat under reflux. Okay, so dilute HCl and heat. Okay, and what we get is we have this hydroxynitrile. 2-hydroxypropane nitrile, and this guy is going to react with H2O, okay, in the presence of H plus ions, okay, and we end up making CH3, CH, OH, CO2H. Okay, this guy over here is 2-hydroxy. Okay, this is 2-hydroxy propanoic acid. Okay, 2-hydroxy propanoic acid, commonly referred to as lactic acid. Okay, 2-hydroxy propanoic acid. So the nitrile can be hydrolyzed. The nitrile can be hydrolyzed in acidic conditions to form a carboxylic acid. Okay, so here the CN is converted to a CO2H. Okay, and we also make ammonium ions. Okay, so we make NH4 plus. Okay, that nitrogen ends up making ammonium ions. Okay, instead of ammonia. If this was just H2O, we'd make the acid and ammonia. But because we have acidic conditions, ammonia is a base. It ends up accepting a proton, and we make NH4 plus. And over here, this should be 2H2O. We can also have alkaline hydrolysis. Okay, we can also have alkaline hydrolysis. Okay, where we can use NaOH aqueous, okay, or KOH aqueous. We can use aqueous sodium hydroxide and we heat. Okay, and in this case, instead of making a carboxylic acid, we end up making the salt of the carboxylic acid. Right, we end up making the salt of the carboxylic acid. So we get this guy reacting with H2O in the presence of hydroxide ions. Okay, and we get CH3 CHOH CO2 minus. Okay, if you wrote NaOH, you can write Na plus over here. Okay, so we get the salt of the carboxylic acid, right? Because it's an alkaline solution, the carboxylic acid ends up being neutralized, right? So it loses this H plus, and we end up getting CH3 CHOH CO2 minus, and we get ammonia. So again, what happens in the hydrolysis of nitriles? Okay, what happens in the hydrolysis of nitriles is that the C triple bond N gets hydrolyzed. Okay, the C triple bond N gets hydrolyzed, right? And then this carbon, the carbon ends up becoming a carboxylic acid, okay, in acidic conditions, whereas in alkaline conditions, this carbon ends up becoming a CO2 minus, right? That's the salt of the carboxylic acid because the acid can lose its proton, okay? And the nitrogen atom in acidic conditions, it becomes an ammonium, and alkaline conditions, it produces ammonia, okay? And we can take a salt of the carboxylic acid, right? This anion over here, this anion, and we can convert it to the carboxylic acid, okay? To the carboxylic acid simply by adding H plus ions. Okay, we can simply add H plus ions. So if we react this guy with an acid, if we react this with any acidic solution, okay, or we just add acid to the solution, the salt of the carboxylic acid will get converted to, or this anion will get converted to the carboxylic acid itself. This type of a carboxylic acid is referred to as a hydroxy acid. Okay, it's a hydroxy acid because we have a carboxylic acid, but we also have this OH group, right? Hence, this is a hydroxy acid. Okay. In this specific example, we have 2-hydroxypropanoic acid, or commonly known as lactic acid. So one last thing to note is that when cyanide ions are used as nucleophiles, okay, we saw them being used as nucleophiles over here in the nucleophilic addition of carbonyl compounds, as well as in the nucleophilic substitution of halogenoalkanes. Right? When cyanide ions are used as nucleophiles, we end up making nitriles. And what we end up doing is we end up getting compounds with more carbon atoms than the compounds we initially began with. So we started with a 2-carbon compound here, and we end up getting a 3-carbon compound. And this 3-carbon compound can then be used to make other 3-carbon compounds.